Final Engineering Wind Turbine Project by Team 2.
Hi everyone, my name is Isabel Soriano, and today I'm going to briefly be going over our project and some of our goals that we were able to achieve throughout the semester. Our main goal for this project was to create a vertical axis wind turbine that provides a sustainable source of power in mainly urban areas, keeping in mind that it needed to be aesthetically pleasing, safe, and having the ability to be scaled if required. Our priority was to generate as much power as possible, but also having it be small enough to not cause any disturbances to the environment, for example, through noise pollution, which can then lead to an ethical dilemma. As for who would necessarily use this, we thought of it being utilized for a backup generator that would then be powered by the wind turbine, which essentially would be placed in homes or hospitals, along with the help of our primary stakeholder, city planners, that will then determine the best place for them. Our project is making use of resources from the environment along with helping the community, but essentially in this presentation, we will be talking about our process creating the wind turbine and the results we got from our prototype and testing, which I will now pass on to Sundari, where she will talk about how all of what I just mentioned ties into the scope and criteria of our project. Thank you.
Hello, my name is Sundari. The scope of our project is to create a compact, efficient, visually appealing vertical axis wind turbine that can be deployed in urban and semi-rural environments. Our design is composed of a hemispherical structure that incorporates 2 layers of cup-like blades. Since it has no sharp edges and has a safety factor of 1.5, it meets our safety criteria. It is also efficiently scalable up and down depending on power needs and installation space. It also spins fast, making it functional to create a lot of power. The sleek, minimalistic look blends in well and doesn't stand out too much. The turbine is also simple to assemble, maintain, and its performance has been tested both physically and through simulations with CAD and CFD. Its performance overall satisfies our criteria and incorporates aesthetics, functionality, good surface area, scalability, simplicity, and safety. Thank you.
Hi, my name is Julian Thompson. I'll be talking about the CAD, which we used SolidWorks for. We went through various renditions, all based on Deal's original design, which was based on an anemometer. An anemometer is essentially just a wind speed measuring tool that has cups to catch wind, and then it measures the speed based on rotation. We went through a lot of different ideas with the scaling we wanted. We also went through the different ideas on how many blades we wanted. We wanted sets of 3, but we figured that 2 rows may be more efficient, which turned out it was, based on the CFD simulations and also the practical model which we developed. We ended up staggering the CAD model and then, staggering the CAD model and then the prototype and testing with CFD, and it turned out that a 60-degree staggered layers worked significantly more efficiently than others that would be lined up directly. We also ended up making a custom bracket, different from what our CAD model originally was, which will be seen on the slides above or below. This sort of bracket was designed to hold the wooden dowels while also holding securely onto the steel pipe, and that's essentially it.
Hi, my name is Savannah Exley, and I'm going to be talking about our prototype. So on the top right of our slide, you can see our original blade design, which was to use 2 liters cut in half to make plastic blades with the top and bottom of a 2-liter bottle. And they worked, but we wanted more surface area, so we switched to our design, which you can see on the left, with cardboard, so that we would get more surface area and it would be less deep of a cup. And then we also switched our bracket from which you can see on the top right to the bottom right, from just wooden to 3D printed, so that we could be able to tighten it and to ensure that it wouldn't slip down the metal rod. And This interacts with the CAD subteam because it's what the prototype is based on, and we use it for testing the CFD, which tests our final rendition of our prototype that we redo the CAD model based on, if that makes sense. And then our MATLAB calculates our data with our prototype's actual data. Thank you.
Hello, I'm Theo, and I'll talk about our CFD simulation. The purpose of our CFD simulation was to see if our model would actually spin before we go on to prototyping in the real world. We tested our prototype at a wind speed of 4 meters per second because that's what the average in Blacksburg, Virginia is. We tested 7 different angles ranging from 0 to 120 degrees because we assumed the torque to repeat after every 120 degrees due to the geometry of our model. The tested models were the parallel blade design and the staggered blade design, which Julian showed earlier. After testing our design, we noticed that on the z-axis, at some angles, there was a higher torque than the y-axis, indicating that our model may tilt, but we don't believe that would be a problem once our model is held into place or made larger and the wind speed wouldn't be as strong or something. We continued to proceed with the staggered blade design, which the prototyping team came to build, because from the 2 images illustrating the CFD simulations, the bottom one is the staggered and the top one is the parallel blade design. While both do have a strong wake, showing that they would both models will spin, the bottom one, which is the staggered blade design, has a heavier wake on one side than the other. So it illustrates that this would generate more torque due to the heavier wake. So we decided to go on with the staggered blade design. And Mohammed will talk about our programming.
Hi, my name is Mohammed, and I'm in the programming section for our team project. We use MATLAB to create 2 scripts. The first script is a power calculator. This program calculates based on 2 methods. The first method is based on results from CFD testing, and the second method is based on results from physical prototype testing. I communicated with both CFD and physical prototyping team to get the input values to then get the potential power output. For the second script is an overspeed detector. This program runs every 5 seconds and it checks the speed of the turbine. If the speed of the turbine is over 15 meters per second, then the turbine is overspeeding. If the turbine is overspeeding 5 consecutive times, then the overspeed warning message is sent. This is done to prevent spam that's typical for while true loops. And an additional feature on top of that is a faulty sensor warning. What it does, it takes the current speed value and the previous speed value, and if the difference is over 15 meters per second, then that change in speed is unrealistic, and a faulty sensor warning is sent to the user.
All of what was just mentioned has helped us achieve our final result for the vertical axis wind turbine. With all of these processes and testing, we were able to achieve the best result in order to generate the most power for our design, along with previously mentioned it being aesthetically pleasing and scalable. Finally, here we have a video of our final prototype actually spinning, and overall that should be it for our presentation. Thank you so much for watching. We hope you have a great day.